In this video, I'm going to teach how to build a full forward pass of a neural network for the handwritten digits dataset MNIST from scratch. Let's begin. These two are from the PyTorch library. This consists of 60,000 images for the training dataset. It's 28 by 28 each image, that many pixels. They're grayscale, so there's no color to it. So this is saying download the 60,000 images. This means do it in whatever folder this IPYNB file is in. The download equals true means it'll download it if it's not already there. The train equals true means it's for the training dataset. If you put false, it'll be for the test dataset. This renperm, it's grabbing the length of this, which is 60,000, and it's picking random numbers from that. And the reason for that is whenever you come down to here and it actually grabs an image, it'll pick the image, or grabs the 60,000 images, it'll assign random numbers to them, to the indexing of them, so that it picks random images. Because if you don't do that, then it'll be in a specific order to start with, and that could bias the data set. So down here, it's the targets. In other words, the Y true, or the what it should be, what the answer should be. Like if one of these images is a 3, then this would come out to be the number 3. So down next is the same thing basically, except it's 10,000 images and it's for the test data set. After the thing's trained, then it can be tested to see how accurate it is. In this video, it's specifically for just the forward pass of the neural net though. Okay, now this is the training loop, which it can be also just called the forward pass. I'll just call it forward, F-O-R-W-A-R-D. So it's, well, I suppose it's not specifically the training only then, but anyway, it's the forward pass. So this is assigning 0 a tensor 0, because later down here, if you try to just put in the number 0, it doesn't work. It wants a tensor. So this one is the batch size. It's how many images are processed at once. One of the main purposes of that is if you have a graphics card, then you want it to be fully utilized instead of just if it could handle 32 images at one time to process, since it has so many cores, CUDA cores in them, CUDA cores or tensor cores, you want it so that it's not only using a small fraction of those tensor cores. You want it to use everything that'll fit in it inside the VRAM, or the virtual RAM, the virtual random access memory. Okay, now this is the input nodes batch, it says. So 32 by 784. So what this means is, remember up here, the 784, it's actually the 28 by 28 pixels flattened. So it'll take 28 rows of 28 pixel values in each row, and it'll, instead of them being stacked like instead of lattice work looking type stuff, it'll stack it into one really long list. So that's where the 784 comes from. And this -1, it just automatically calculates how many in this dimension there are whenever you reshape things to make the numbers come out right. So once you have everything over here except one of the dimensions, then you can put -1 and it automatically should calculate the dimension, or the data, to make it work right. Okay, now down here, it's doing a batch at a time. So it's saying what size is it, this part is. So this is taking the train image tensors from up here, the train image tensors, and it's saying grab however many in a batch size at a time, which is 32. And right here, it's making the number smaller so they don't throw everything off by getting too big. It's just dividing by 255 because the maximum value of each pixel is 255, which comes out, it's 0 to 255 is 256 options, which comes out to be 8 bits. So it's specifically called an unsigned 8-bit integer. That's what a lot of images for neural nets work off of. Now down here, the hidden layer nodes. So if you remember the dot, if you look up a neural network, you'll see dots and then lines connected to the next layer of dots and so on. This is basically the next layer of dots. It's 128 dots in that one layer, like going up and down. And this is the weights, which are the connections between the first dots all the way on the left and these dots, the lines that connect them. That's what these are. And this is something that makes the numbers work out better. It's okay. Now this is actually doing the calculations, because you have the inputs times the weights, and you would typically add a bias number to it, but I'm not going to do that right now because it doesn't communicate how it works as well at the moment. So anyway, this does matrix multiplication, specifically dot products in batches. That's what matrix multiplication is. And dot products are multiplication and addition. So this is a lot of what neural networks do right here. So what it's doing is it's taking each row of data and it's multiplying it by, it's element-wise multiplying it. Well, you can look up videos specifically for how the dot products work, and I believe I have a video on my channel about that too. I might link it at the end of this video if I remember. So let's see. So torch stop maximum, what this is doing is it's calculating the rectified linear unit activation function. It sounds complicated, but it's really just the maximum of 0 or whatever it went into it. So specifically what it'll do is, if you have, just say the number 3, 5, -1, it'll just leave the 3 like it is, the 5 like it is, but the -1, it'll just turn it to 0. If anything's negative, it'll turn it to 0, like -23. It'll just turn it to 0. And if it's positive 23, it'll just leave it like it is. So that's what this does. And the 0 that I was talking about from earlier, the tensor 0, it's right here. If you try to put the number 0 in, it just doesn't work right. Like, watch. Do that, run it. See? Must be tensor, not int at this line. So I'll undo it, put it back, run it, and it works. Okay, so now this is just basically a repeat of this. Then, well, if you look on a neural net, this would be the third layer of dots on a picture of a neural net. Down here it's doing the same thing, except right here it's 10 on this last layer, 10 dots. This was 64 on the previous layer. This is the last, or the output layer. That's why I call it out nodes. And it has 10 dots in that visual illustration. The reason for it is because you have 10 categories of images. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are 10 things. So that's why that's 10. So this, I'll just remove it. Okay. Now, so anyway, this is basically quite a bit of a repeat of that. All right, now if I come down here, notice that this one has ReLU after these 4 lines. With these 4 lines, it doesn't have ReLU. And the reason is because using a different function called the Softmax function. And here it says probabilities, but it can be called Softmax also. So I'll just call it Softmax, SOFTMAX, and change this up, make sure it's correct. Softmax, oops, SOFT max. Okay, so make sure it still works. Yep. So what this is doing is taking the natural number e, that's a number found in nature a lot. It's to do with continuous compound interest as well, and it's raising it to the power of each of these outputs. These outputs specifically are batch size of each of the predictions. Okay, so this is for one of the images. It's predicting this. They're not normalized numbers, so they look weird, but it's predicting the highest value is right here. Nope, sorry. Highest value is right here, which is the digit 9, because this is representing its estimation, saying what image is this. And there's 10 of them here, because there's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's what that's doing. And this is grabbing the next image. You remember I was saying like it parallel processes like in the CUDA cores in the graphics card. So it's doing multiple images at once. So it's fully utilizing it to save time and it makes stuff more efficient. So, or it's more fully utilizing it. So this is the next image, and it's saying, what image do I think this one is? In this case, it thinks 9 is the answer also. Down here, 3.5, that looks like the highest number in this. So that's a 0, 1, 2, 3. So it thinks the image is a 3 in here. It's just randomly picking at the moment because the numbers are randomly assigned. Like if you look up here, torch.randin, it's from the random normal distribution. And that's where it's picking the numbers from. So this is taking the natural number e, which is about 2.71828, and it's raising each of these to that power. So if I go e to the logits, then it should come out with the, well, hold on. To simplify it, I'm going to index at just one of these. Okay. Now, excuse me. Now, I'm going to simplify it more and just index to that. All right. Now, if I say e to the logits, or torch.e raised to that, it'll come out with 2.36. Now, if I say e to the logits, e to the logits, index 0, 0. Well, this first one came out with a different number because it's randomly picking from up here and so on. But notice how these are the same. The torch.e raised to the logits, index 0, 0, and e to the logits, which is torch.e to the logits, index 0, 0. So these are the same thing. So it's taking e and raising it to the power of whatever the output is from here, the logits that it showed earlier. And to show that it's doing multiple at a time, I'll just remove this, and this is for each image. So it's saying e to the whatever prediction it thinks this is, or however likely, or whatever it thinks it's a 0, the image. And then e raised to however likely it thinks it's that. And so more specifically, if I do logits index 0, comma, do this. So it's taking e raised to the negative 0.9, or about 0.9, and it's coming out with that as the answer. So I can actually prove it by doing this. Say, well, I'll just actually put the numbers. Well, I showed this first. Torch.e, it's about 2.71828 it should show. Yeah, 2.71828. Okay, so now I'll just put 2.71828 raised to this number, and it should come out with pretty close to 0.4076. Yep, 0.4075, which rounds off to 0.4076. So that's how that works. And so I'll erase this and delete this to clean it up, then run this to clear that. Okay, keep everything clean. So this, anyway, once you have the batch of things converted to converted to, or e raised to the logits, then you can more simply use this for Softmax. So the reason it's called Softmax partly is because it'll show the maximum number, but it's not only like a binary type thing saying the maximum number is, I'm 100% sure it's one certain number and it's nothing else. That would be like a maximum. That would be a maximum. But a soft maximum says, okay, I'm 80% sure it's this number, 2% sure it's this number, and so on. And where all the percentages come out to, if you add them together, totals 100%. So that's what Softmax does, and that's why it's called that. That's part of the reason. What the Softmax is doing is taking e to the logits, each element inside there, like this one and this one, etc., and it's dividing it by the sum of all of the predictions in each image. So, for example, this is the first image, and it's predicting this likelihood or whatever that it's a 0, a 1, a 2, a 3, and so on. So it's saying out of all of these, what percentage likelihood is it this? What percentage likelihood is it this? And so on. So if I if I run this, it should show something that totals 1 or 100% whenever you add this together. All right, so I'm going to run the Softmax and scroll up to here. Okay, now if I take all this and add it together, I'll just do it. First I'll index at one of these to simplify it. The numbers change because it's picking random numbers up here. So, and it's not trained either at the moment. So what this is doing is it's converting things to percentages. And to prove that, if you do .sum, then it'll add all of these numbers together and it should equal 1 or really close to 1, making room for rounding errors and floating point arithmetic. Yep, 1.0. So this is saying for each, just say if this is image number 1, it's predicting about 6% likelihood that it's a 0, 1% likelihood that it's a 1, 68% likelihood it's the number 2, and so on. And so all those percentages come out to 100%. So that's what that's doing for the Softmax. This was the forward pass, and I'll mention this real quick, the loss function, and a quick overview of what it's doing. It's taking the negative natural log of this, and it's calculating the average of that, so it gives you one number, so that you can say the loss of this full batch is 3.47, so, or 3.447. So the goal is to get this loss as close as you can to 0, and that's what the training of the neural network does, and this is how you know how well it's succeeding. What this is basically saying is when you put an image in, just say the number 3, and it shows the likelihood from the Softmax of, just say for this first image, it shows that it thinks it's most likely the number 0, but you don't care what it thinks is most likely is unless it's the correct answer. So 0, 1, 2, 3. So if the answer is actually 3, then what you want to do is grab just that, 0, 1, 2, 3. So the way you could do that is, so I'll put this down here so it doesn't reset with random numbers from up here. And so if I do index 3, since its predictions and the indexes are the same, I mean the correct numbers and the indexes are the same because it's arranged that way. So 0, 1, 2, 3. So it should show 0.1566, or it thinks it's about 15% likely that the answer is 3. Just say if it actually is 3, which this would show what it actually is, then you only care about that one prediction, because remember before, hold on. Okay, there we go. Remember 0, 1, 2, 3. So 15% likely. So if I put the 3 index into it, so about 15% likely it's a 3. So what the training should do, what the purpose of the training is to increase this number, its prediction likelihood, as close to 100% as possible. Right now it's about 15% sure it's a 3. And if it actually was a 3, then it would do the loss, the negative log loss, to give you and the system a number to work off of, to be like, okay, now optimize this neural network. And the way you can tell you're optimizing it is by make the loss as close to 0 as possible. So that's the goal of the neural network, is to make the loss as close to 0 as possible. And that involves the partial derivatives and a lot of other stuff. Some of it's not as complicated as it may sound, and some of it's a bit complex. It's mostly just a lot of simple pieces combined together, but a whole lot of them, and figuring out how to combine them. So that is the forward pass of a neural network, with a quick mention of the loss function and how it ties in with the forward pass. If you have any questions or comments, let me know, and thanks for watching. Please click like and subscribe, and hope you have a good day. Thanks. Bye.